Okay, so today we're going to look at an area of engineering that is very unique, fun, and still in a lot of development, and that field is smart manufacturing. So here's what we're going to discuss today concerning smart manufacturing. First, we're going to introduce the idea and then see what it comprises of, as well as some applications. After that, we're going to discuss the changes and how information has been flowing, as well as the innovations in tech that have led to this point. Finally, we're going to examine some trends that are then leading to the new future opportunities, as well as some skills that engineers might need to be able to adapt. So, as I've developed a new understanding of different engineering components, one aspect that has really attracted me is controls engineering. Within this field, I have had the opportunity to combine a vast array of different components together with robotics, human interaction, vision systems, and a plethora of sensors into a seamlessly functioning machine. I've gotten to experience some of this out in the field when I was working with the quality engineering department at John Deere in the factory where they produce their engines. There, I saw the significance of using sensors to better monitor all components on the line. That way, it is easier to attack different problems that arise as it gives you a very specific location, which in turn helps you better the quality control of the entire line. From this, I got very fascinated by mechatronics, which has helped me better understand these sensors and their purposes. These skill sets are extremely influential in the overall idea of smart manufacturing. So before beginning, a crucial term that we need to understand before we can understand smart manufacturing is IIoT, which is the Industrial Internet of Things. This is a large uh, branching tree of a company, factory, or workspace that combines all of its devices, sensors, networking components, and applications that work together to collect and analyze data through synthesis. This can be seen in the image on the screen on the right side, has all of the different kind of components that work together, and on the left side is all of the consumer IoTs. This is the core value of smart manufacturing, as the NIST, the National Institute of Standards and Technology, defines smart manufacturing as fully integrated, collaborative manufacturing systems that respond in real time to meeting changing demands and conditions in the factory, supply network, and customer needs. So that really encompasses IIoT. So this is where IIoT is so influential. To properly have a smart manufacturing factory or workspace, it requires mass amounts of information that is constantly developing and changing from different technologies that input information. This is sometimes something that makes smart manufacturing unique and how it is going about its revolution, as it is often called Industry 4.0 manufacturing, where the 4.0 is a reference to the fourth industrial revolution. The first revolution was obviously steam, the second, electricity, and the third, basic automation and computing power. And this one is still the blossoming of those two things intertwined computation, physical systems, and intelligent technologies, both a new lens. So, what makes this such a unique addition into the scene is that it has no intention of blowing up the old status quo. It is just implanting new computing power and automation to further what is already in this factory design, redefining the manufacturing goals to be more efficient and effective using the proper tooling. So, what are the technologies that actually enhance smart manufacturing? We know that there need to be a variety to send enough data to the IIoT sensors to make them usable in quality engineering. There are a few different critical components that go into building out the smart factory to reach its ultimate levels of smart manufacturing. The first is industrial robots. These include things like articulated robots, Cartesian robots, welding robots, and many others, including one that I actually presented on in my last project, the hexapod machine robot. Each of these robots has a litany of sensors and actuators that allow real-time adjustments based on human operator changes or work line conditions, such as a slower line. These together create production monitoring systems which build out the IoT sensors, which allow for tracking important metrics like cycle times, errors, and task operation. That way, engineers can adjust it based on what they are seeing. This is exactly the space that I got to work in my internship. I got to see some real-time updates on an articulated robot. Um, and we had to adjust based on its error rates, and we were able to make minute changes based on it. On the other side, if the robots are not grounded but freely moving around the floor, they are considered AGVs, or automated guided vehicles. These are the tools that move materials, semi-built components, and fully built components through factories. These self-guided vehicles, like forklifts, navigate routes using sensors like GPS and collision detectors so that they can navigate appropriately and move the parts around quickly and efficiently. Similar to industrial robots, they utilize sensors in the production monitoring systems that allow engineers to track how they're moving, see their inventory, and most importantly, optimize their routings so that they can reduce bottlenecks that pieces aren't getting stuck in transition. So then in terms of actual fabrication, there are some tools that work seamlessly with smart manufacturing. The first is CNC machines, or computer numerical control machines. They're precision machining tools that are capable of manufacturing complex parts. These really encompass a lot of what we have discussed in class, such as lathes, water jets, milling machines, laser cutting, drilling, and many, many more. However, the difference is that they are all now CNC specified, meaning that it is already preset and being completely performed by a pre-specified computer program. Then back to our production monitoring system, the manufacturers are able to track the performance of each piece by seeing its cycle time, tool wear, and other quality control issues, meaning they are able to optimize the machines and repair much more effectively by knowing what exactly is going on with the system. The other fabrication tool that is very effective at integration in smart manufacturing is 3D printers, which are called additive manufacturing. At this point, 3D printers are well known for their ability to build out objects by using layers of filament, including things like prototyping and tools to create end-use parts. Here, production monitoring systems of the IoT allow the manufacturers to track how much material has been used, the quality of the print, and catch failures before it's disastrous. And this optimizes some of the most common complaints of 3D printers, i.e., their speed and frequent failures, to make them more effective and seamless within industry use. So then, kind of taking a look at the trends of how smart manufacturing has blown up and why it shows no signs of slowing, and it's arguably the biggest reason is that it alters how the needs of the customer are being met. A large discussion in 2024 and well before that is how trust and confidence has shaped the industry after years following COVID and some upheaval in society's status quo, where customers want more communication and a relationship outside of just having moving the money to the point manufacturers are now more of a service provider. Therefore, through developing smart manufacturing techniques, the manufacturers have much more um, influence and specification how they manufacture their products, meaning they can provide more specific products to customers, as well as generally have more information for the customer as they are receiving more data. Then, on purely the production side, smart manufacturing gives engineers a better advantage in keeping things running as they have many more tools at their disposal through IoT to monitor and examine the machine's health. As established in the technology section, engineers have so much more data than before, and it becomes so much simpler to work predictively and seeing when the failures will arise as opposed to always having to react to the problems. So it's clear that smart manufacturing is not slowing down in terms of its integration into factories, and it's steadily rising and developing still. Current manufacturing systems lack much of the functionality that smart manufacturing bring to the table, which can kind of be seen in the figure to the left, where we've got self-configuration, self-optimization, early awareness, and decision making, all seen in the figure on the screen. All seen in the figure on the screen. Where the current state is much more underdeveloped and has massive potential for growth. From the article Challenges, Opportunities, and Future Directions for Smart Manufacturing, a state of art review, it was found that accommodation and food services have a tendency to automate by 73%. And then manufacturing, transportation, and warehousing industries have the potential to grow automation by 60%. So this means smart manufacturing processes have found their niche in society, and it's time for them to enhance it. One way that it is being accomplished is being seen everywhere else in the world at the same time, which is AI. When we talk about handling lots of data, AI is now the tool that comes to mind, and it is no different here, as you can use it to take all of this data from IIoTs and quickly leverage it to build out analytics that might take normal users hours to sift through. So machine learning is the next component rapidly being added into smart manufacturing, and it is quickly turning into a stable, as correct prompting and understanding allows for much more knowledge on the system and now in its prediction. So this is where it's important to understand the skills that should be developed as an engineer to become an expert within the smart manufacturing field. This comes down to two main aspects. So you have the hardware and the software. First and foremost, it is important to continue developing knowledge of all types and machining components and between machining components and robotics, as they are crucial based on what we saw in the technology section. As without their understanding, you don't understand what different components are actually doing, so you can't use any of the data to make educated adjustments. Secondly, it's important to develop software skills, specifically in AI training, as it is established that it is blossoming very quickly. Moreover, having a rudimentary understanding of PLCs or programmable logic computers would allow for understanding on the back end of task management in factories, as well as being able to parse mass flux of incoming data correctly to then use your engineering skills. Both of these aspects are extremely important to develop simultaneously, as by understanding the system and then the controls to them, that encompasses the entirety of smart manufacturing, and it makes you a smarter engineer. So factory life is adjusting again, as it does with every stage of revolution, and we are entering the fourth. So we have found a way to combine technology and machinery to a new level to give engineers more data and information than ever before. And with that allows for new innovation, new understanding, and new engineering solutions previously never even thought of. This is an exciting time to be a young engineer, especially one like me who loves to do control work, as by combining intrinsic software skills on the back end and engineering intuition and an understanding of machinery on the front end, it allows for smart manufacturing to enhance production, quality, and performance throughout the world over. So thank you so much for watching. Here's my appendix. I hope you have a great rest of the day.